In this lesson, we'll be learning how to deal with probabilities involving numbers. So to tackle probability involving numbers, we don't draw Venn diagrams. We draw a probability tree instead. And I'm pretty sure most of you have seen this, something related to this before, where we're dealing with principles of addition and multiplication. So just to refresh, a probability tree will look something like this. It starts off at a node and ends at a certain event. So let's say event A and event not A. And from then on, it's a separate node to event B and not B, another node to event B and not B. Okay, there are several properties involving the probability tree. So if you look at the first one, the probabilities leading to each node must sum to 1. This is actually stemming from each node. So if I were to look at this node, this probability of A plus probability of not A, the sum of it should give me 1. And the next probability is that each subsequent event is entirely dependent on the first. So if I look at event B that occurs secondly, then it completely depends on event A occurring first. And hence, this is actually a conditional probability idea, which we'll go on later in this lesson. But first up, let's look at the mutually exclusive property of the probability tree. Mutually exclusive events occur as branches from the same node. So if I'm looking at this from event A to not A, since the branch diverges from the same node, you can either go along this path or you can go along this path, but you can't go along both at the same time. And this is the reason why event A and not A are mutually exclusive. Because of this, the probabilities along the branches are always summed up by the addition principle. Now let's talk about the conditional probability of the probability tree. Do take note that if an event is said to have occurred first, then the conditional probability is simply the probability at the next node. What does that mean? It means that if I were to illustrate it, again I'll use A not A, B not B. If I were to just look at it simply like this, if I were to ask you the probability of B given A, then this conditional probability here is simply the probability of whatever that's represented along this branch. So if let's say this number is the probability is 0.4, then this conditional probability is simply 0.4. Because this goes back to our understanding that B is dependent on A having occurred already, and hence this probability is not the probability of B. So take note, this is not the probability of B, but it's in fact the probability of B given that A has occurred already as we go along this path. However, if an event is said to have occurred secondly, then the conditional probability is slightly more complicated. So if I were to reverse this example, okay, right here, if I were to reverse it into probability of A given B, since B has occurred secondly, but it has said to occur already, then we need to look at all the branches. So we have branch to A, not A, and again here is B and not B. We have to go along both branches, so look at my arrows from here to here and here to here, and sum these two probabilities up. Okay, then that will be the denominator for which A intersect B is divided by. Sounds confusing, so let's look at an example to illustrate this. For this question, you might want to pause the video at this point and try to draw out the complete probability tree in order for us to solve the next question. And since we are dealing with an event that has occurred secondly, so take note that the word given is here, right? So that is a huge signal that conditional probability is involved. The test is positive. This is our second event, and that the person has the disease. So having the disease would be our first event. So give it a try and let's move on in a few seconds. What I've done here is to draw the probability tree. And I think yours should look similar to this. Remember our question, it's to find the probability of D given T. And as you can see, the event T or not T occurs after the event D. quite a few people confuse this as, oh, isn't this just 1 over 200 multiplied by 0.9? Then that is wrong. Okay, in fact, what we should be doing is to consider this. Using our formula from set notation, we can expand this into PD intersect t over pt. And using our set notation knowledge, I'm just going to write it at the side. Pt equals to pt intersect d plus pt intersect not d. So if I were to write it here, the full thing will be pd intersect t over pd intersect t plus p not d intersect t. When we have this, it's quite easy to understand that we have to find all these elements, right? And these elements are simply going along the probability tree and finding the probability. So if I were to find the probability of d intersect t, then it's going along this branch, then going along this branch. So when I multiply these two probabilities together, that would give me probability of d intersect t. And similarly, if I want to find the probability of d intersect not t, this would just be going along this path and going along this path and finding, okay, so this one would be the probability of not d intersect t. So to combine the two together, you realize that the answer is 1 over 200 multiplied 0.9, right, going down these two paths, over 1 over 200 multiplied 0.9, I'm just going to bracket it, plus 1 over 199 over 200 multiplied by 0.02. And this should give you an answer of 0.184 rounded to 3SF. Do take note that the important property here is that these events, d and t, are independent events, which is the reason why you can do this multiplication via the multiplication principle. So if events d and t are not independent from each other, then that cannot be possible. So let's recap. We have shown that probabilities involving numbers are best solved with probability trees, and it's easier to visualize and be able to see conditional probabilities with it. We also have talked about mutually exclusive events and how to solve conditional probabilities, especially when the event that is said to occur has occurred secondly instead.